Okay, sir. So, warm welcome to all. Today is the day 2 for the student workshop on virtual labs and tools, SWVLT 2021. The day 2 session actually starts with the means talk on Multisim and its applications as used for the virtual labs and tools. It is mainly aimed for the students of as well as some students of the ECE department. The first half of the talk will be delivered by Mr. Surajit Mukherjee sir, who is also faculty of our department from AIT. I hope that with this valuable talk and this intellectual session, all the students and the registered participants can gain advantage from the talk. And already the list of materials and the downloaded link have been sent to the respective groups and the students mail ID. So follow the lecture, and at the end of the session, if you have any doubt, please post on the YouTube live chat. Your questions will be addressed at the end of the talk. So now I request Mr. Surajit sir to please preside over the talk. A warm welcome to you, sir.
Thank you, Tilak sir, for the introduction about the workshop. And first of all, I am thankful to our departmental members, especially head of the department and other faculty members, to provide me the opportunity to present a lecture on this workshop. And I will talk about Multisim. So before starting, I just want to mention Utkarsh Bhaskar. One student has been joined. I don't know how the students get the Zoom link. So Utkarsh Bhaskar, please ask your friends in your group to join on YouTube, and you also join on YouTube. Utkarsh Bhaskar.
Okay, sir. Yes, sir.
Yeah. Please circulate among your group that please join on YouTube. Okay.
Okay, sir.
Thank you very much, Utkarsh. And others, I would request Tilak sir to check the waiting room and kindly admit our faculty members. Okay, so
once again, I am requesting to all the students kindly join on YouTube. The link has already been provided. Coco and Redmi, Renita Paul, Selina Khan, Sutrina Mondol. These all are students. Kindly join on YouTube.
okay, so let's start.
Sir,
Tilak,
can
sir?
you? Yes, sir. Yes,
Yeah.
sir. You please.
Thank you.
Continue the
So
talk.
you please check the list, that is the participant list, and admit our faculty members and
Okay.
remove the students. Okay.
Okay, sir.
So very good morning to all my respective faculty members and my dear students. So in this SWVLT, that is students works on virtual lab and techniques. So in this case, in this particular workshop, so what our objective? Our objective is to do a practical lab from our present location, that is from our home, or either I am located at PG. So using my desktop or laptop, or in some cases it can be a mobile phone. So using those devices, how we can realize some lab experiments related to the your curriculum. So one of the major platform for simulation of circuits, different types of circuits, that is NI Multisim. So NI is stands for National Instrument. This NI stands for National Instrument, and the Multisim is the name of the software. So myself, Mr. Surjit Mukherjee, I am presently as an assistant professor of ECE department, Haldia Institute of Technology. So through this particular session, so I hope you can able to understand that how we can realize and lab using a multisim. Now, what is multisim? So multisim is an industry standard based in class 5 simulation environment. Okay. So basically, this is practically used for industry. So there are some advantages of using this multisim. So it is circuit teaching. It is the cornerstone of the NI circuits teaching solutions to build expertise through practical application in designing, prototyping, and testing electrical circuits. So what we can do, we can design it, we can prototype it. There is another part of the multisim that's known as Ultisim. Okay, sorry, Ultiboard. Another part of the multisim is Ultiboard. So using Ultiboard, we can design one PCB for any particular circuits. Okay. তাহলে so why this multisim required for UG course? Now this is the virtual platform, so virtual lab environment that what using this multisim lab environment we can what we can do, we can do different types of labs such as basic electronics, analog electronics, digital electronics, circuit theory, analog communication, digital communication, and lastly the different types of projects we can realize using multisim. So before we make it harder design, so we can do with the multisim. So this is a very versatile platform where we can realize the circuit before we realize it physically. So once if we do not design using multisim, so we after calculating different parameters, mathematical calculation, say suppose we design a circuit. Now that circuit you design using a breadboard. circuit design using a breadboard. Now, there may be some required that something required that we need to change some values of the resistance. Maybe we need to change some values of the capacitance, or we may need to change some ICs or transistor. So that will not be possible once you design a hardware. Sometimes it is very difficult to pick out. So after soldering, it is very difficult to change some components. So this should not be happen using this multisim. And we can realize the different types of lab, as I mentioned, that using multisim. Now, what I do today is that I will give some of the experiments related to your different labs. I'm not going to discuss in detail of different labs, but I will take some experiments. So you will get a basic idea about how we can design using multisim. Then we will go, then after practicing several times, you can do at your own. Now, how to use Multisim? That first you need to download Multisim, that is from ni.com. That link has been already shared with you. Another thing is that you can do online simulations using multisim.com. There you have to sign up, and after that you can design a circuit. So I will show you in both the cases, in the installed environment and in the online environment. Okay, and for design one circuit, so there is a user manual, so you can download it from this website as mentioned, and using the user manual you can easily design any circuit. Now I have chosen 5 experiments for today's discussions. So the first experiment is the study of VI characteristics of PN junction diode. So this is very popular experiments and very common experiments that actually done in the first semester or second semester. Actually, in first year, we generally do this lab. So study of VI characteristics of PN junction diode. So those, if the final year students are present in the live chat or YouTube live, so then they can easily understand that how they have done the lab by using physical components and some power voltage sources and multimeter using those components. So this is very common experiments. So next experiment is the full wave rectifier with filter. So that is also a very common experiment, and it is very useful because this full wave rectifier is everywhere used in your electronic component design. So without we have AC power supply at our home. So our electronic components running on DC power supply. Now that AC to DC conversion, that we need to rectify that AC to DC conversion. So we need full wave rectifier with filter. So that is very much useful circuit that in every electronic gadgets. Okay. Next is the common emitter BJT amplifier. That we know that amplifier is also a common part. So suppose we are talking on your mobile on some microphone at some program. So what we do, there are some boxes that where we can hard the sounds. The system present is known as the amplifier. So there the input signal from your from the microphone is amplified and it has been forwarded to the speaker. So this is very much an useful application circuit, that is common emitter BJT amplifier. Another circuit is the inverting amplifier using 741 op-amp. So 741 op-amp is very much common for any type of circuits design and any type of amplification circuits. So 741 is very common for our lab purposes, and for any die projects there we can use 741 op-amp. So every projects mostly we use 741 op-amp, and very popular ICs since it has been introduced in the electronic gadgets. So I will show you how to design an inverting amplifier. And another experiment is the astable multivibrator. So astable multivibrator, that is also very popular. We know that we use clock circuit. We use clock generators. So using astable multivibrator, we can generate a clock signal. So basically the clock signal is like a square pulse. So that is a clock signal. So using the clock signal, we can see the using a clock signal, we can generate any counter circuit or any type of circuit where some clocks are required. So these are the basic 5 experiments I will discuss, and I will discuss how to do it with the multisim, right? So first we start with the study of VI characteristics of the PN junction diode. This is a typical lab circuit which is used for lab. Here you can see that there is a power supply VS dependence. VS we sometimes is called VCC, and that is a variable power supply, and we have a diode 1N4007. It is very common or popular to for our labs 1N4007, and across the diode we need a voltmeter, and we need an ammeter in series with a resistance with the diode. So this is basically a forward bias configuration. This is basically a forward bias configuration. Now in the right side, what we can see that VI characteristics of a silicon diode. We know that for silicon diode the cut-in voltage is the 0.7 volt around. Okay, and for germanium it is around 0.3 volt. So as I writing to the mouse, so it is may not be proper. Okay, so that is the forward bias configuration. I am not going to discuss the reverse bias. So as we know that for reverse bias there is now minor changes on the reverse bias, and if we increase very high voltage, it causes breakdown in the case of reverse bias. So here is one point comes that, so whenever we do some practical circuits in our lab, so there is a high chance that our components may burn out. Sometimes we may increase the voltages. There is no control over that. Sometimes so the students face the issue that I have seen different times in my experience since the last 10 years. So it happens, but in this case there is no such issues, and you don't have to worry that whether the circuit components will burn out or not. So we can easily design any circuit using the multisim. So what we do, we need to design the circuit using multisim, and we need to characterize this VI response. Okay. Now this is the multisim window, right? So in this multisim window, what we do, we have to find the components, we have to connect those components, and we have to characterize. So first of all, you just see here on the top there is a icon place, there is a tab place. So at place there is component. Okay, So whenever we click on component, there are some groups are shown on the left side. There are groups are shown on the left side. So these groups, we can see, if I click on groups, then we can see sources, we can find basic, also we can find diodes, we can find transistors, analog, TTL, CMOS. Also there is some MCU microcontroller units. There are some advanced peripherals. There are some mixed signals ICs. There are indicators. There are also electromechanical components, such as motors. There are connectors, and there are some NI components. So we are not going to discuss all those details in this 1 hour program. What we do, we have to take the components that is required for our purposes. So first of all, what we can see in our circuit, what we can see, we can need one voltage source, one ground, one diode, one voltmeter, one ammeter, and 1 kilo ohm resistance. So all these we will connect as shown in the circuit. Now from the sources, first we take the sources. So what type of sources? Power sources. Now what type of power sources? There are different types of power sources. We can take DC power sources. You can see that there is a symbol of the DC power source. Now click on OK. So we have DC power sources, and it back to the component window. Okay. We need, what do we need? Ground. This ground. Again, click on OK and place here. Okay. So we got power sources. We need, we got ground. Okay. So next, what do we need? We need resistance. What amount of resistance? 1K. By default, it is at 1K. So click on OK. I take 1 kilo ohm resistance. Next, what do we need? We need diode. So there are a lot of diodes are present. So that is 1N4007. You can click on diode, you will get different types of diode. You can click on Zener diode, you get different types of Zener diodes, and all this SCR, photodiode, LED, you can see. Now diode 1N4007. We can scroll, then we can get this 1N4007. You take 1N4007. Now what do we need? We need an voltmeter, ammeter. Okay, so these are not the components. These are the measuring instrument. Voltmeter and ammeter are not the components. Those are measuring instruments. So that have to take in different way, right? So now all the components we have taken. Okay. Now we have to rotate this. So as this is a fixed voltage source, so we can use a variable resistance in series with the fixed voltage source. So that will give you the variable voltage source towards the diode. So from the place component, take component. Now go to the basic. Now at the basic, there you can see variable resistor. So from variable resistors, You click on, say we need 1K, that is sufficient. So we take a 1 kilo ohm resistors, variable resistors, then close. Now these variable resistors will be in series with the voltage source. Now what we do, we have to connect the components. Now just by hovering this pointer at this N terminal of the component, we can see this, this is bulleted form. You click over there and drop over another N terminal of the another component. Similarly, from resistance to diode, click and drop from diode to this load resistance. So this is basically load resistance, right? And from load resistance to the ground terminal, drop. Now we can change the value of this load resistance just by double clicking over the load resistance. We can change the label. So this is written as R1. So we can write RL. Click on OK. So now it is, we can see that it is RL. And so we can say it is VR. The stands for variable resistance. Okay. So we got this. The design is complete. Now what we do, we have to place the meters. So we have to delete this line, the connection, because we need to connect an ammeter between the diode and the load resistance. So ammeter will be in series. So we just select and delete it. Now on the right side of your window, there are some right side panel. You can see there are some system components are present. Now if I am hovering over there, you can see there is this multimeter on the top. There is multimeter. So I click it. So multimeter comes. Now we take a positive terminal to the diode terminal and the negative terminal towards the load terminal. Now this will be an ammeter, so we have to change it. So we need to calculate the current. So click over A by double clicking. Once again, I am showing you. By double clicking this multimeter, we have to click over A, and this is the current will be DC type. So this is DC type. If the current will be AC type, so you have to click on this sinusoidal signal, sinusoidal symbol. Okay. Now what we need a voltmeter. So take another multimeter, place over here. So voltmeter will be in parallel with the diode. So we are connecting the voltmeter. Now this voltmeter, so we can see this is a voltmeter and this is a DC type voltage it will measure. Okay. Now the circuit is complete. Our circuit is complete here. Okay. We have a variable voltage source. We have a voltage source and we connect a variable resistance such that we can vary the voltage source. And we have the diode along with the in parallel with the diode there is a voltmeter which is XMM2, name is XMM2, and XMM1 is the ammeter which is connected in series with the diode and the load resistance 1 kilo ohm. Say we change the voltage, the value of the voltage source 20 volt. Okay. Now we can see that we can change the value of the variable resistance. See, by using your mouse, or there is a key. So using A. So I am now pressing the A key from my keyboard. So you can see that it is changing. Okay. Next thing is we have to simulate it. Before that, I save this circuit. So save this VI characteristics of PN diode. Now my circuit has been shaped. We have to simulate it. Now there is a simulate icon. Click on there. Now there is a run button, or you can use your F5 to directly run it. Now I'm running it. Now you can see the voltage across the multimeter. You can see the current across the current through the diode, voltage across the diode, and current through the diode. Now if we go on increasing, now the resistance value is 1K. So voltage source along with the 1K gives the current, this amount of current. Now now the resistance have the maximum value 100%. You can see this is 100%. So maximum it has reached the maximum value. Now if we scroll it or minimize it, so the voltage across the diode is increasing. And current across the diode will also increase. Clear? So let's stop this. There is a red icon on the toolbar. There is a red icon. We can stop it here. So let's stop it. So let's change the value 1K to say suppose 10K. Okay. Now again we run it using F5. I think showing 19 milliampere. Okay. Now go on increasing the resistance. The current across the diode is decreasing and the voltage is also decreasing. Clear? Now so by suitably varying the value of the load resistance, so if we change the load resistance value, say load resistance value at 50 ohm, okay, now there will be some changes on the now you can see that the voltage across the diode is quite high and the current across through the diode is also quite high, because due to the load resistance the total current is limited. So that's why I have reduced the load resistance. Now this facility cannot be possible, or it is very I cannot say that it is cannot be possible, but in our lab whenever we do this virtual in physically, so we have to remove it and then we have to connect another one. We have to check, okay, that is not doing properly, then again we have to change it, again we have to connect it. So this is quite a difficult job, or it is say more than time consuming. So here within few minutes we can easily find this. So using 50 ohm resistance we can easily find this. Now if we go on increasing the resistance, we can see that the value of the current is also decreasing and the voltage across the diode is also decreasing. Okay, so these are so you have to take the measurement and you have to plot it using the graph paper. So in table form you have to calculate the write the voltage and current and you have to plot it. Now this can be done easily using this multisim. So you don't have to take you have to change the value of the resistance, then you have to note down the value of the voltage and current, then again you change resistance, then again you note down the voltage and current. No need to do those things. just by a simple thing we can do that. Okay, so I am showing you that one. So I have so this is a simple circuit. Okay, this is a very simple circuit. There is no voltmeter, no ammeter, no variable voltage source or variable resistance. So by this same circuit, what we can do, we can get a VI characteristics of the diode. Now how, you just see. Now please follow. I am click on over simulate on the toolbar. Now click on analysis and simulation. Click on analysis and simulation. Now what we have to do, we have to sweep the DC voltage source. We have to sweep the DC voltage source, which is denoted as V1. We can see that is denoted as V1. So what is the sweep value? The start value is 0, stop value is 5, and the increment value is 0.01 volt. Now the output, what do we take the output? We take the current across R1. So the current across R1 will be the same as the current across D1. So we can take ID1 or we can take IR1, any value we can take. Okay. So from I select on IR1 and then add. Okay. And then we have to save this. Now at this moment you run simulate. Yes. Now you can see this. Now you can see the VI characteristics of the diode. So I have chosen from 0 to 5 volt. If I take from 0 to 10 volt, then the graph will be more steep. Okay. Now what we can check? We can check the where is the cutting voltage. So on that we click on cursor, show cursor. Here is the icon cursor. We click on show cursor. Now the value of the cursor position is shown on the right side. So the moving the cursor. So up to you can see that X2 is 479 millivolt and Y1 is very low. Sorry, Y2 is now at 1.259 millivolt milliampere, and the diode voltage is 617, and sorry, the source voltage. The below is the source voltage, and this one is the current. Now the source voltage is go on increasing, and the current is go on increasing. So this will become the VI characteristics of the diode. So again, click on simulate. Now from the DC sweep, we take the output. We can take the voltage across the diode as V1 and current across the resistance R1. We can save it. Again, we can run it. So this is the voltage across the one terminal, across the diode. So one terminal, basically this terminal across the terminal across the diode, and that is the current. Okay, so we can see that voltage and current and gradually increasing. So this is the DC sweep. So we have to take the DC sweep from the simulate analysis and simulation tab, and we have to take the what are the source, what source we have to vary, and what output we want to plot. Okay, so we can take, now we can extract the data for our purposes. So what we can do, tools, export to Excel. So if we take export to Excel, so what will happen, the data will be stored as an Excel file. Now you can plot it on your own, or also using your graph paper. Using Excel you can plot also, and using graph paper. And there are a lot of options. You can take copy graph, so we can copy the graph and we can save it in a Word file for our lab manual preparation. So I suggest you, for lab manual preparation, please take the graph for Excel file as Excel file, take the graph values as Excel file and plot it using Excel. Okay. So you can, there you can change the different parameters of the plot, right? So this one is basically the VI characteristics of the PN junction diode. So we can get that for 0.7 volt. For 0.7 volt, we can have the changes in the current. Okay, so here it is actually the voltage across the diode, but what we have plot the variable voltage source, the value of the variable voltage source, and the diode current. What we have plot in the multisim, we have plot the variable voltage source and the diode current. So we have to change that, how to plot that variable voltage source. Now for that, actually what we have to do, we have to plot the voltage at 0.2. I just add it here and just remove it, V1. Now save, run it. Now using cursor, you can take the measurement of the values. Okay. So you by this another terminal where you can take that this is the voltage probe. So what we can take, we can put a probe. So if I run it, sorry, just we have to cancel it, this one. So how to cancel it? We have to analysis an option. Now on the DC sweep, interactive simulation, and keep on interaction simulation and save. Now run it. You can see the voltage across here. So it is 11.2 volt, because there is a voltage drop of say 0.8 volt, 0.8 volt voltage drop due to this diode. So using voltmeter, we can see using ammeter probe, stop it. Now using ammeter probe, now again run it. Now we can take the current also. We can check the current also. That is, the current is 200 milliampere. It is due to the direction of the current flow of the ammeter probe. So the current is 200 milliampere. So this we called as a probe. So here we can see the voltage and current at any point of the circuit by using probe. Okay. So this one is the VI characteristics of the diode. So here we can take the manual measurement across the diode, and we have to plot it, or in other cases you take those values on the Excel sheet by using this simulate and DC sweep, and from there you can take the values. So basically what you have to do, you have to you have to take the voltage at V2 and the current with D1. Okay, so these two voltages, whenever you will get, so that you will plot and check the VI characteristics. Okay, so you practice it. The next experiment is full wave rectifier. So full wave rectifier using with filter. So full wave rectifier with filter, that we can realize some of the predefined labs, predefined experiments on the Multisim. So samples. So there is a blue folder icon. On the blue folder icon, I click. So those are the samples. So on samples, you click over power conversion. What we need to convert? AC to DC. Now you can see that's control rectifier. Click on that. So this is basically a control rectifier. So that is using SCR. So I have to close this. So this is not required. Now click on power supply. There is a circuit which is known as power supply. So power supply will give you all the details. Now here you can see this is the power supply. So rectifier is the important part of the power supply. Clear? Now there is a voltage source. That is 120 volt RMS, 60 hertz. So this is basically a default voltage source. Whenever you take the source, on the click on the sources and power sources, that AC power. Okay, you can click over there. You can see that the 120 volt RMS, 60 hertz is the default voltage source. So using a transformer, T1 is known as the transformer. Where we can get the transformer? So we can click on the place component and click on the basic. On the basic, there you can see that is transformer. So that is transformer. So on click on the transformer, then we can see this, the transformer. Transformer, and there are diodes, 4 diodes. That is bridge type rectifier. This is a bridge type rectifier. It's not a simple full wave rectifier. I have shown you a full wave rectifier. I have not prepared that demo circuit. So this is basically bridge type rectifier. and there is a capacitor filter that is 200 microfarad. C1 is the capacitor filter. Just a minute. There is a capacitor filter, and there is a LED, and there is LM317K, that is a voltage regulated IC, regulated voltage. At the output we can get the regulated voltage source. Now what we want to do, we want to check that whether the rectified output is working or not. Now, so this one is the oscilloscope. XC1 is the oscilloscope. So the oscilloscope we can find on the right side. On the right side you can find this oscilloscope. Okay, so leave this XC1, that is by default. So how do we check? We will check that whether the output is rectified or not, filtered or not, and of this full wave rectifier. Now we can run this circuit. Now we'll check a double click over the XSC2, and we will pause this on the top panel. We will pause this, and we can vary the scale. Here we can vary the scale. Here we can vary the position, say Y position. Okay, so we have changed the position. So what you can see that the output is filtered output. The output is filtered output. Okay, at the end of the full wave rectifier with capacitor filter. So that is the filter output. And what is our input? We can check the input also. If we stop it, we connect the second terminal with the input, and again we run it. Now click or double click over XSC2. Now you can see that what is the input here and what is the rectified output here. Rectified filtered output, not only a rectified output. So that will be a rectified filtered output. Clear? So we can see using oscilloscope. So what we have to do, we have to connect the oscilloscope knob. Those who have done physically these labs, basically 5th sem and 7th sem, if you are listening this PPT or listening this webinar, then you can easily understand that if you are do this lab in your physically, so there are a lot of problems. So the probe is not connecting properly, the voltage CRO is not working properly. There is some problem on the CRO. There is some problem on the probe. There is some problem on the power source of the kit. So a lot of problems are present, but here is no problem. So you have to just design it, and you have to simulate it at your own, at any type of circuit. Okay. So there are a lot of versatility in this Multisim. So if you practice it, you will learn a lot, and your theoretical knowledge will be more clear as you do practically. So without practical knowledge, without doing practical, your theoretical knowledge will not be clear. So for that, you have to do that practically. Okay, so I'm closing it. Now, what we do here, we use this XC1 oscilloscope. Now we are unable to extract the data from this XSC2, this oscilloscope. There is another oscilloscope is present that we can see that Agilent on the below, that is Agilent oscilloscope. Now this one is the Agilent oscilloscope. There you can see this is Agilent oscilloscope. And this terminal, this is channel 1. If you don't understand that which one is channel 1, which one is channel 2, just double click over it. You can see this, the get up the view of this oscilloscope, and from there you can understand. You can see this one have some changes. So as we connect with one, there is one terminal have some changes, and we connect this terminal at this terminal here after rectifier. Now we run it. Click over after run it, we double click on the oscilloscope. We have to power on the oscilloscope. Now we can see that the signal is present. That is channel 1. Channel 1 is the input signal. Now if we click on channel 2, we can see the rectified filtered output signal. Okay, we take a single value and we can measure by using cursor. So we move along y-axis using this terminal. We move along x-axis by clicking over here. It will need a practice. So if you practice a lot, then you can easily do any experiments. Okay. So we can see that there is some phase difference between the rectified output and the input signal. Okay. There may be some phase difference, but whether that is for both the peak, that is for positive peak and negative peak, the output has been rectified in the positive side, so we are getting a positive signal. Okay. So from here we can take the value. You can see the value here. Okay. If I click over y, so we can check the value for y1 and for y2. So if we move y1, if we move y2, click on y2. Okay. Take the value, or you can acquire the waveform. If I click on acquire, normal, now save. This icon is known as save. Save. Now the power supply.dat as .dat file, that the data will save. So there you don't have to worry about that data, and you can from that data you can easily plot it. Clear? Click on this. There is a floppy disk inserting icon. So click on that floppy disk inserting icon, then click on save. Then you can take the data. Okay. So using this Agilent oscilloscope, we can take the data. Now stop it. And so this one become a power supply. My next type is the common emitter BJT amplifier, and I am quickly go through this just within 1 or 2 minutes. It has been already designed, and I will just open it and show you. Now BJT common emitter amplifier, I'm opening it, and what we have to do, we have to characterize the response, frequency response. we have to characterize the frequency response of this amplifier. It has been amplifying. There is no issue with that. But up to which frequency it can be useful? From what is the lower cutoff frequency and what will be the upper cutoff frequency? That is the important for the case of any amplifier. So that graph, we need this graph. We need this graph for the case of amplifier. So that can be done using this simulate analysis and simulation icon. Now here you can see the AC sweep. AC sweep, what we take from 1 hertz to 100 megahertz. A broadband, the frequency will shift from 1 hertz to 100 megahertz, and for each decade it will count 100 points. And what will be the output? We need the power. Actually, we have to calculate the gain, so we need the power. So if we check the power, then we can easily understand. So I have added here PR5. So R5 is this one is the R5, 8.2 kilo ohm. So we click on the R5 and PR5 and add. I have already added it, and I just save it here and run. Now you can see the graph what we have seen in our in the PPT, that has been easily obtained using by a single click. And there you don't need to do a lot of calculation or a lot of measurements. Just by a single click, you can take the frequency response of an BJT common emitter amplifier. So you can see that there is a phase. So we can see that there are some phase noise. So we have to eliminate those frequencies where we have a lot of phase noise. So basically, between this point to this point, the amplifier from 1 kilohertz to 10 kilohertz, the amplifier will be useful. And beyond 10 kilohertz, there will be a lot of phase noise may occur, and that will not be useful for may not be useful for some applications. So if I have an audio amplifier, then the phase noise is not desirable. Okay, so that is an BJT common emitter amplifier. Now you can see that all the graphs are already present, so I am just deleting all those. Now this is our record values. Now from tools, we can export to Excel and we can plot it at our own. Clear? So that is the frequency response of an BJT amplifier. Now what we can see that whether it is amplifying or not, we can just go to the analysis and simulation and go to the interactive simulation and save it. Now click over this run icon and click on it. Okay, you can see this. The output voltage is around 48 millivolt. Now what is our input voltage? You can see the input voltage 0.001 volt means 1 millivolt. So 1 millivolt is our input voltage and our output voltage is 48 millivolt. So using this particular circuit, there is a gain of around 50. So basically, if we calculate peak to peak, so 50 and 50, basically 100. So gain is around 100. So beta for this amplifier is 100. Okay. Now you can use Agilent oscilloscope and you can take the data. And the next is the inverting amplifier using 741 op amp. It is very much popular. Now I'm going to just see you in quickly. Just open it, go to the op amp inverting amplifier as I have already designed it. Now this is LM741H op amp. 741 op amp is very common to you. I have taken a voltage source of 0.1 volt RMS and the frequency is 1 kilohertz. Now actually this one is running, so another is not, will not be running. So now go to simulate, the analysis and simulation option. I'm going to that. I'm going to interactive simulation. Whether it is amplifying or not, I just have to check this one. Click on Agilent, turn on it. Now you can see. So at one we have given the input of the Agilent channel 1, and at channel 2 I have given the output. So this one is the input. So we can see that there is a change in the phase. So when input is low, the output is high, and when input is high, the output is low, and also the output is quite amplified. If we go to the cursor, then we can see that Y1 it is 126 millivolt, the peak of it, and for the input the peak is at 85 millivolt. For the input it is 85 millivolt peak, and for output it is 126 millivolt peak. Clear? So you can easily take the data as I have already mentioned from this Agilent oscilloscope. So that is, and op amp inverting amplifier, the output is the inverted of the inverted output is inverted of input, that is the opposite of the input. And my next point is astable multivibrator, and those who are on second year, you may not heard about astable multivibrator, or you may be, but you soon you will see about astable multivibrator and you will experience it. Now astable multivibrator is basically a clock signal generator, and I have shown the circuit, and the circuit has been already done using this, and you can see that if we run it, now you can see. So this is the square wave output of the astable multivibrator. Square wave output of the astable multivibrator. This sloping curve is the voltage across this capacitor. So basically this capacitor is responsible, and this resistor is responsible, R3, and this C2 is responsible, that is known as duty cycle. So for duty cycle we have to change those values, okay, and based on that value the time period for the positive peak and for negative peak will be decided, okay. So whenever you that has been discussed, that theoretical study will be done. In the theoretical study you can easily understand. So that is known as the 555 astable multivibrator, and this IC is known as IC 555 timer. So if you go to the Google, and you can find that IC 555 timer, and this circuit is also available everywhere. And this is a basic circuit of a stable multiplier. So using this multism, we can do a lot of things, but there is some time constant. So due to that time constraint, I cannot discuss a lot of all the things. There are a lot of things are present. I have not discussed about digital circuits. Some of you have already done the digital circuit using multisims. I hope that you have already experienced a lot of issues, and if you have uh, any issues related to multisim or circuit design, you can always welcome to communicate with me, and my email ID and mobile number is present here. And for any queries, you can communicate with me, and that is the WhatsApp number also, so you can drop a message on WhatsApp. And if you are not able to install the multisim at your PC, so I can help you with that installation file, offline installation file through Google Drive sharing, and soon I'll share with you. And okay, so for today, I hope you have get an idea that what is the advantage of a multisim to calculate different circuit parameters, to design a circuit, and in future using multi-board, that is one part of the multisim, we can directly design one PCB for the components are present. For there is some limitations of multisim education versions, that we cannot use more than 25 components at a time for any circuit. So mostly for our practical applications or for our lab purposes, it can be easily done using 25 circuit components. And for high level circuit design, we may require that more than 25 components. Okay, so thank you for your presence. Thanks to students, and my students is my inspiration. So if they can easily understand, and if they can do at their own, and I'll be happy. And thank you, HOD sir, and the organizing team member of ECE department for providing me opportunity. I am honored. Thank you, sir.
Thank you, sir, for the wonderful talk that you have given on the multisim and its applications for the electronic circuit analysis part. Now, just few queries are there from the students part.
Okay.
Can I take them?
Yes.
Okay, sir. Like Ayush has posted one question like, among multisim and P-Spice, which is more preferable?
So in SPSpice, what you have to do, you have to write the code. You have to write the code. Okay. Basically, Multisim is a spice simulation software. So we can extract the SPSpice model from one circuit. From one circuit, we can extract the SPSpice model. So in Spice, we have to write the code, but in Multisim, we can take directly components, and we are simply just joining the components. And we have.
So here we are not at all using any coding context also. So that is the greatest advantage of the multisim. Okay, well, suppose one more question is there, like any other alternative like circuit maker or like this kind of simulation tools?
Yeah, circuit maker. Circuit maker is okay. We can do using circuit, but the problem is that it's not versatile as multisim. The versatility of multisim, if I use a paid version or pro version of multisim, so there will be a lot of versatility. Then we can use an RF component also, and we can use microprocessor also. So in circuit maker, we cannot use microprocessor. So for microprocessor, we have to use the other programs.
Okay, sir. So once again, sir, I take this opportunity to thank you on behalf of the Department of EC for the interesting talk, and that also with live demo that you have given regarding all the electronic circuit components starting from diodes, transistors, and all.
So
So
I request all the students that to practice it. Otherwise,
yes,
they will not be familiar with the different tabs where we can find it. So for one component, you can find in source. Another component you can find it for digital IC. You have to go to the 7.4 series, and that you have to do
yes, yes, yes,
practice. Hmm.
yes, yes. Okay, sir. So all students just note down the means the download link in case you want to install that. And in case of any queries or doubt, you can also contact sir. Sir is always willing to help you from the students' point of view. All these events and all, they're only for you only. If you are satisfied, then that is the main objective. So once again, sir, I heartily thank you. And
Thank you, sir. Thank
in
you.
the second half, the students will be having the respective lab schedule as already intimated. So I end this session now. Shall I
Yes,
end,
yes,
sir?
yes,
Okay,
yes. Thank you. Thank
okay,
you.
okay, sir. Thank you. End kuchi, huh?